And this is the shader itself. I am using the, I'm just assuming a say again? No. I'm just assuming a rectangle that's facing right to left. So X is on the left, or from left to right, and Y is from top to bottom, from bottom to top, sorry. And the values are in 0, 1, and it's angle independent. The texture coordinates don't care about the angle where our rectangle is oriented at. So the center going down the length of the beam is increasing on the X, and the other way is increasing on the Y. And I'm using a lot of functions in here like exponential. I've got a sign in here somewhere. I thought I did. Got this, which gives you -1, 0, or 1, depending on the sign of the value. I have pow, and I'm going to show a shader I got here. So this is what is this? Function 3. So this is x to the y. So this is the pow function. And going from x0 to x1, you see it's kind of flat early on, and it goes up really quickly, right? And I'm using that in this to basically detect the ratio of our noise-based height to the pixel position. So the height of the pixel from the center. I get a scale factor, and this may be less than 1, 1, or greater than 1, this ratio. And I'm subtracting it from 1 so that way the ratio will be close to 0 in the center. And as you go, it'll get larger and larger until it's over 1. And I'm using it to calculate the white value. So it's slightly different from a square root because it's taking the power to the slightly less than 0.5 power. And I believe I don't think I used those same values in here, but this is demonstrating the way a power function behaves. If you're under 1, like if you take 0.2 times 0.2, you'll get. Sorry, if you take the square root of 0.2, you'll get a bigger number back, a larger number back, because you had to multiply a larger number by itself, but they're both under 1, so they would shrink, right? And when you hit 1, if you take the power of it, you'll get 1 back. If you go over 1, you'll start going up really quickly. So what that does is the white stays pretty bright near the center, and it gradually fades off until it hits an even ratio between the y value and the height, and then it drops off abruptly, and the other color takes over. Does that make sense, or should I explain anything else?
I don't know about anybody else, but yeah, I mean, conceptually, it makes sense.
I love Charles's answers.
Well, I get the concept. I mean,
I know what you're really doing over there, Charles.
What's that?
You're doing like sine, cosine, and your head you go.
Yeah, I'm doing it all in my head.
Oh, there's the inflection point. Okay, yeah, I got it.
The inflection point.
Exactly.
So I do have. I'm I'm not using the logarithm, but I had it as an example. Let's see if I can. This is the binary logarithm.
I tell you, by the way, I love being able to visualize these things because that kind of helps. You're right, a visual representation of what is actually happening. Because when the thing's moving, you're like, oh, that's a cool effect. But
it's hard to track it with the mouse.
right. See how it's waving right here.
So this is a logarithm like what Ed brought up. It's at this is actually at 1 because at 0 it breaks. The logarithm isn't defined at 0, but this is 1 plus x, and it kind of ramps up and then it levels off very quickly. And the binary logarithm is if we're taking powers of 2, it's how many times you had to loop to get that power. So early on, say you had 16, you would have to take 1 and multiply it by 2 4 times. As you get to 1 million, you have to do it 20 times. So it doesn't grow that fast. It levels off quite a bit after this. And I could probably show that, but I'd be screwing with numbers and I might mess it up while I'm doing it. Sine is... I have my cheat sheet of which numbers looked decent.
I was going to ask you that before. Is there like a cheat sheet? Is there a place where somebody's already figured out, these numbers and said, or you just have to kind of do this all on your own?
Well, this is a pretty special purpose shader, but you could find examples of the numbers computed at. There's all kinds of tables for this because when we didn't have calculators, all the engineers wrote these giant books filled with these numbers.
Right.
What is that number? I got to go look it up. Especially the logarithms. All the astronomers were making these giant books.
So you could get yourself one of those books, right? I mean, is that what you're saying?
Right. There's tables of numbers.
Yeah. Okay.
And let's see. So Barry was discussing the phase. This is the y value. You can see what that looks like as you move it. You see the sign is moving. It's kind of moving slowly, but. And we've got number of periods. So this, you can do this to contract it, or to go the other way. This is the offset, so this is the height. I guess I should have called that amplitude. But,
amplitude, yeah.
So, there's quite a bit of variability with sine. And because it's so regular, that's one of the things I mentioned that you're getting basically the same function just shifted as you move. So you can mod the numbers and still get the same results. So you mod by 2 pi, but your input might still go wild.
Because you're getting a repeating pattern. Is that what you're saying? I mean, you've got from the lowest peak to the highest peak is pretty much the pattern, and then it repeats itself, sort of inversely, I guess you could say, or from lower peak to lower peak, if you wanted to do it that way, and then it just.
Yeah, they sometimes call these troughs and peaks. Oh, and the inflection points are here, Ed. Because never mind. So, and exponential is the last one I have.